But now we will go to the first session today, which is challenges for PSC, and we will start with Professor Gonzalo Guillén Gosálbez. I'm not going to read all your CV. I will leave more time for you, so it will be a very short introduction. Professor Gonzalo, he did his studies in Spain, and now he's associate professor in chemical systems engineering at the Institute of Chemical and Biochemical Bioengineering at ETH Zurich in Switzerland. His research interests focus on process optimization of sustainable industrial systems using mathematical programming, machine learning, and life cycle assessment tools. So with that, I will let Professor González talk, and he will talk. And you can see the title of his presentation, Process Engineering for Chemicals and Fluids within the Earth's Safe Operating Space. Remember that at the end of the lecture, we will not take questions at the end of the lecture, but we'll collect all of them at the end, and we will have plenty of time for the discussion. So please keep your questions so that we can have a very good discussion. Thank you.
So thank you for the kind introduction and the invitation to the workshop. So today I would like to talk about how we can actually combine process systems engineering with industrial ecology tools. Yeah, so in essence what we do is we tackle different types of problems here. So from the molecular levels, starting in the lower scale, process design also in the context of supply chain management and also micro-scale systems. So what we do is we develop mathematical tools in order to address this type of problems, where the key point is that we're going to include sustainability criteria in the objective function of our models. I will give you examples later during the talk. These models are quite complex, so we also have to develop some algorithms in order to identify the optimal solutions, and then these solutions later on are passed to decision makers. Here we can think about policy makers, scientists, engineers who will use these solutions in order to improve the sustainability performance of different types of industrial systems. Yeah, so here to be more precise, so we use multi-objective optimization. So we have here optimization problems with a multi-dimensional objective function. We include cost, but also the different pillars of sustainability, environmental metrics, and also when possible as well the social performance. We have equality and inequality constraints that are used to model the system. So we have, for example, mass and energy balances, specifications on variables of the problem, and then we optimize both continuous variables as well as discrete decisions. I will give you examples later in the lecture. So one of the key points is how we can actually So one of the key points is how we can actually quantify the environmental impact, and in order to do that, we are using life cycle assessment. So the key point here is to focus on the entire chemical supply chain. So instead of just focusing at the plant level, we consider the impacts of all the echelons in the chemical supply chain, so including the extraction of raw materials, the production itself, storage, distribution to final customers, and also how to handle the waste once the product has been used. So finally, we have inherent trade-offs here in this problem. So not just between economics and environmental impacts, but also between environmental categories. So the solution of the problem is given by this so-called Pareto frontier. So the starting point tends to be suboptimal. We optimize for minimum cost, for minimum environmental impact, and then we generate all these Pareto solutions of the problem. So the key point is starting from the starting solution to modify through changes in the operating variables and the design variables to modify the system in order to operate always in an optimal manner, considering the different sustainability criteria that we include in the model. So this is the overall framework, and we have applied this to many different types of problems at different scales. So let me just give you an example. In the context of supply chain problems, this topic was somehow discussed before in the previous one. So this is a problem that was first proposed by Professor Niels in Imperial College. It's just an example of how we can actually use these tools in the context of specific sustainability problems. So let me give you a flavor of how it works. So here we have to design a network in order to produce and deliver hydrogen to the final customer. So we have different technologies to produce hydrogen, to store hydrogen and transport hydrogen. In this case, is the United Kingdom. So here we have to pick up the optimal combination of technologies, decide where to establish the different plants in the UK, including also the capacities and also the flows between the entities of the supply chain, right? So this will be a standard flow. Now we have to do that considering different criteria. The first time to minimize cost, but at the same time to minimize environmental impact. So this includes again the selection of technologies, capacities, locations and flows between the entities of the supply chain. And this needs to be done considering again environmental impacts and economic performance. So how can we actually solve this problem using process systems engineering? So in essence we follow two different steps. The first one is to create this so-called substructure. So this is a mathematical representation where we have all possible alternatives to our problem. So for example, we have different technologies for production, as I mentioned before, different technologies for storage and also for transportation, and here we consider all the links between the different nodes of the network. So here we have millions of alternatives that are considered in this mathematical representation, and then we will use optimization in order to identify the optimal portfolio. So this is done using a mixed interlinear programming problem where we have, again, a multi-objective objective function with different indicators, right? So I will elaborate further in the next slide. We have mass balance equations for the different nodes of the supply chain, and also we have capacity constraints for the supply chain entities as well. And then we have equality and equality constraints, and then continuous variables as well as discrete decisions that we have problems. I will not explain in detail the whole formulation. Let me focus on how we include environmental aspects in the mathematical model. So this is explained here in the next slide. So first, remember that it's essential to consider the impact in all the echelons. It's not just the emissions of the chemical plant, but we consider all the echelons in the supply chain. And in order to quantify first emissions, what we do is to connect the continuous variables of the problem with some data that we will take from environmental databases, in this case, Guillén. So for example, we have variables to denote the amount of hydrogen produced, stored and transported. So these are continuous variables in the problem. And then we multiply this with, again, some information that we take from databases. Here we are using Guillén, which was developed in Switzerland. So for example, in the model, we have a variable that represents the amount of hydrogen produced via a technology, for example, steam methane reforming. And in Guillén, we'll find the life cycle emissions of producing hydrogen with this particular technology. So we multiply both, and then we get the total emissions. So once we have these emissions, we can convert into impacts. So here in this first work, we're using the indicator 99. There are many LCA metrics, and later I will talk about the use of planetary boundaries in the context of assessing these technologies. So we first calculate the life cycle inventory of emissions, we multiply with some characterization factors, and then we have, in this case, damage to human health due to climate change, which is quantified using this indicator 99, which is following the LCA principles. So finally, we have a complex MILP. So just to give you a flavor, we have thousands of binary variables and equations. And if we just try to solve this problem straight away in a modeling system with some standard branch-about methods, it takes a lot of time. So we also have to develop some decomposition algorithms to accelerate the search. I will not get into the details today. Just let me show you the type of insights and the Pareto points for this particular problem. So here we have cost, here we have environmental impact, and the algorithm will automatically determine these solutions. So here, again, we have a portfolio of technologies, different locations, and also we optimize the flows between the supply chains. And this is done automatically by the optimization algorithm. So this will be the minimum cost, the minimum impact, and in between we have many more alternatives that are then automatically provided by the transfer boundary method coupled with the compositional. In general, what we try to do here is to operate in these regions of the Pareto front, where we can reduce the environmental impact to a large extent without having to sacrifice too much the economic performance of the system. And we have applied this approach to many different programs where we always follow the same type of framework, starting with the construction of the superstructure, mathematical models, and then algorithms to identify optimal solutions. So for example, these are some instances that we solve. In the case of designing biofuel supply chains, this is actually a collaboration with Argentina, with Universidad Nacional de Tucumán. In the context of petrochemical supply chains, also going down into the process design level, for example, multi-utility optimization of heat exchange networks. We also have the optimization of biofuels facilities for bioethanol and biodiesel, and also in the context of batch processes in pharma, where you decide sequencing, batching, and different types of scheduling decisions, considering economics and also environmental impacts. So this is pretty much what we have been doing in the last years, and now we'd like to switch to the current research, where the focus here is to try to connect all these decisions that we make all the way to the planet level. So how to optimize and understand the broad implications of any decision that you take in engineering, right, at the planet level. So this is the main focus. So let me motivate why this is important. So life cycle assessment has become the prevalent approach, I would say, to quantify environmental impacts, and you have more than 100 metrics in the literature, so you can choose among many different types of indicators. The problem with these metrics is that they are very useful to compare technologies, but they don't really tell you if these technologies are sustainable in absolute terms. So let me give you an example here. So let's say we have two chemical groups to produce one particular chemical, A and B, and then we use an LCA metric to compare these technologies. So we can conclude here, for example, that B is better than A, but the standard metric will not tell you if these technologies are truly sustainable in absolute terms, because it could happen that both are sustainable or none of them or only one of them. So this is just a relative comparison, but it is not really giving you the insight of whether these technologies are sustainable when you deploy them at a scale globally. If you want to answer this question, you need a threshold. So you would have here a maximum impact level such that if you have this maximum impact again, such that if the technologies exceed the threshold, then you can conclude that they are not sustainable, and if they operate within the threshold, right, so this is the so-called self-operating space, then you could conclude that they are sustainable. So here it's not just a relative comparison, but rather you are comparing the impact level with the ecological capacity of their system. So it's not only between the two technologies, but rather at the global level. Now, how can we actually carry out this type of assessment? So in order to do that, we are going to use here this framework of the planetary boundaries. This was proposed in this paper, famous paper in 2009. The idea is that there are 9 Earth system processes that regulate the resilience of the planet. So one is climate change. We are very concerned about climate change, but this is not the only environmental category of concern. So we have other environmental impacts that are critical. For example, biosphere integrity, ozone depletion, the release of novel entities, aerosol loading, the chemical flows of nitrogen and phosphorus, the consumption of water, land system change, and ocean acidification, and all together they regulate the stability of the entire Earth system. It's not just about climate change. So for each Earth system process, they define 2 different planetary boundaries. So the first one separates the safe operating space from the uncertain zone. So the safe operating space is a region where we could stay for many centuries to come, so the impact levels are not that large. If you start increasing the impact, you transgress the first boundary and you enter into the uncertain zone, where there is an increasing probability of destabilizing the Earth system process. And finally, you continue to increase the impact further, then you enter into this high risk zone where there is a very large probability of shifting the equilibrium state of the planet to a new state, which most likely will be less friendly for humanity. So right now, just to give you an idea, 6 planetary boundaries out of 9 were already transgressed. So there is indeed a strong motivation to develop tools, algorithms that design systems to operate within the safe operating space. So this framework was not developed by engineers, rather by environmental scientists. So we have actually to adjust this approach to be used in the context of engineering. So how this is done is by following 2 different steps. The first one is called the downscaling step. So you have here to take the global ecological budget and you have to assign part of it to the process that you want to investigate, right? So this is an ecological cake that we should share among all anthropogenic activities, and we have to take part of it and assign this share to the process that again you want to evaluate. There are different ways in which you can do that, and this step is quite controversial. For example, you can follow a utilitarian sharing principle. In essence, the more you contribute to the economy, the more you are allowed to produce. So this is the gross value added of the process, and this is the GVA of the total economy. And once you do this, then later you can calculate the impact of your chemical system, and now you can compare with the threshold. So if you exceed the threshold, you are sustainable. If you operate within the share of the safe operating space, then it will be sustainable. So we have a systematic algorithm that will take one industrial system and will be able to classify as sustainable or not in absolute terms based on this approach. So now, the first thing we did with this was to go to the eco-image database, and we took 500 chemicals from eco-image that are currently produced from fossil carbon, and then we quantify the impact on several planetary boundaries. And here we consider a wide range of chemicals, for example, fertilizers, pesticides, fuels, pharma compounds, polymers, and compounds. So what we found is that almost all of them are unsustainable. So 99.4% of these chemicals are unsustainable. So this is essentially what we found. I'm not going to get into the details. I'm just providing some chemicals here. Where you have propylene, ethylene, you have gasoline, diesel, you have ammonia, sulfuric acid, methanol, and so on. And here I'm showing the different planetary boundaries, the carbon footprint. And the color in red denotes the transgression of the planetary boundary, and in green that you operate within the safe operating space. The problem here is that there are these planetary boundaries that are systematically transgressed heavily by the fossil chemicals, climate change, ocean acidification, and biosphere integrity. The reason being that they are very sensitive to the CO2 emissions, and then chemicals production from fossil carbon emits large amounts of CO2. So this is clearly saying or telling us that we have to do something in the chemical sector, because the way we operate right now is not sustainable. So we have to retrofit operations in order to stay within planetary boundaries. Now, let me elaborate further on what is happening here. So this is the linear production model of the chemical industry. So we take, in essence, carbon out of the ground. We convert this carbon into chemicals. We require large amounts of energy that are coming from fossil fuels, so we emit CO2. But also, once the chemicals they have been used, they are disposed, for example, plastics in a landfill or incinerated, so therefore they will release the fossil carbon that they contain. So this is not a sustainable system because of climate change. We could think about, for example, closing the carbon loop here, and this can be done in different ways. For example, chemical recycling. Right, so taking the polymer waste and recovering the monomers. We can actually use CO2 capture as feedstock, or just use photosynthesis to capture the CO2 and then use the biomass as feedstock in chemicals production. For example, let's focus on CCU, right, and check if this would indeed help to operate within planetary boundaries. This is in essence how the system will look. So on the left we have the standard production scheme, where we take mostly oil, coal, and natural gas to produce methanol and indefinite cracker, olefins, and aromatics. And alternatively, you could also think about a system based on green methanol, where you capture CO2, you combine with green hydrogen, electrolytic hydrogen powered by renewables or from biomass. And once you have the methanol, through methanol to olefins and aromatics, you can produce the same platform chemicals that you would actually generate from fossil carbon otherwise. All these technologies are high TRL. They are ready to be deployed, but as you will see in a minute, this would be expensive. So all these, again, technologies are not just low TRL technologies, they are very mature. So this solution on the right is feasible, I would say. Now, we took, as a first step to quantify impacts in these two systems, we first started by determining the impact of current fossil platform chemicals. So we took olefins and aromatics and methanol, the way they are produced right now, and cradle to gate emissions are around 1 gigaton per year. Now, this is very, very important to highlight. When you compare 1 gigaton with 40, 50 gigatons, the current emissions levels, perhaps this is not much. But if you compare with the safe operating space, which is 4 gigatons, what this means is that we are consuming a quarter of a planet to run the chemical sector. So the emissions of the chemicals from fossil carbon, they represent 25% of the maximum allowable emissions. So again, this is telling us that it's important to retrofit the chemical sector. If you move to solutions based on CCU, you could go from 25% to 1%, but this is very expensive, as you will see in a minute. You put here the cost of different scenarios based on renewable carbon, and this is direct air capture that is powered with electrolytic hydrogen from wind. You can see here how the cost is almost 3 times to 4 times the cost of the current fossil chemicals. However, this is also interesting to highlight. This is another analysis that we did for methanol, considering the peak of prices in natural gas after the Russian invasion of Ukraine. And as you can see, at some point there was almost parity between the fossil methanol and the green methanol. So due to geopolitical factors, the fossil resources, they are subject to a very large volatility in terms of economics. And at the same time, we could expect that the green route will improve because electrolyzers will improve and also renewables will become cheaper. So yes, today the green route is very expensive, but in the future, let's see what happens. So it's highly concerning. So we have applied this to many different problems, including planetary boundaries in process design, supply chain optimization, also a lot of work in ammonia production and in the production of electrofuels as well, where we follow the same approach. And we are able to produce these radar plots where we quantify impacts and compare with the safe operating space. So very quickly, in the last slides, I would like to talk about the extension of this framework to incorporate the Sustainable Development Goals. They were proposed in this famous agenda in 2030. So there are 17 SDGs that cover the 3 pillars of sustainability. We have again climate change, but also there are others connected with the consumption of water, ecosystems, human health, and so on. So now the question is how we can actually take decisions considering the SDGs. So this is done using LCA and also absolute sustainability concepts. So here we are building a substructure of the chemical sector. This is a sort of simulator of the chemical sector right now with 20 different chemicals, where we have decisions in terms of the source of carbon, the type of energy that we use, and then we can formulate an optimization problem considering objectives that are connected with the SDGs. We have also mass and energy balances and capacity constraints, and we can interrogate the model to find the best ways to produce chemicals sustainably. Yeah, so very quickly, so this is a first analysis of the fossil industry, which is consistent with what I discussed before. The impact on SDG 13, so here we have 5 SDGs because not all of them can be easily incorporated into this optimization framework. So the impact on climate change is quite large, but on the other indicators, the performance is not that bad. If we try to reduce impacts in climate change without looking into other indicators, we find solutions that they can lead to burden shifting. So you can reduce the impact on climate change, but you can have some collateral damage, for example, in particulate matter and toxicity. However, if you include all the SDGs in the objective function and you control this collateral damage, you can find better solutions. They are more balanced. So So you reduce carbon emissions, but you keep this collateral damage within some acceptable levels. Now, how this is done? So through hybrid production, so all these technologies, they have complementary strengths. There is no silver bullet to combat climate change. You should, from our viewpoint, combine fossil, CCS, biomass, chemical recycling, CCU, all together to some extent. So finally, before I go to the conclusions very quickly, so very quickly here, what I wanted to mention, this is a merit curve where you have the different chemicals, how much CO2 you can avoid, and the cost. What we find is if you want actually to retrofit the chemical industry, the cost could be around $150 per ton, or even cheaper if you use biomass and chemical recycling, right, by closing the carbon loop with these methods I mentioned before. The other option is not to do anything. Let's just operate the chemical industry as we are doing right now. What happens then is that you will have then to remove the CO2 from the air if you do nothing. But removing CO2 from the air is very expensive. So here I've been very optimistic using bioenergy with CCS and direct air capture. So it's $200 per ton, but direct air capture is much more expensive, all the way to $600 per ton. So what we want to do to retrofit the chemical sector or to not do anything, so I would argue that the first is much cheaper. So with this, sorry that I extended a little bit, I go to the conclusions. The main take-home message I would say is that this process systems engineering field provides a very powerful framework to handle and to tackle different types of sustainability problems. I think this is a very exciting area to work, and I will be happy to discuss with you further ideas for collaboration. So with this, I will not acknowledge, of course, the hard work of all the lab members, and particularly these were the people whose work I presented today also. And most of this was also funded by the NCR Catalysis project in Switzerland. So with that, thank you very much, and I will be happy to take questions.
So thank you very much.